In this video, we're going to walk through a couple of vector applications. So this is the first in several videos to look at different ways that we use vector knowledge that we've developed. So the first one is, let's think about something being pulled in three directions. There's lots of reasons this could happen. If I teach chemistry, we might be talking about atoms and electrons and ions being pulled by each other. If you're talking about physics, maybe you have some different masses that are involved in the situation. But I'm going to draw in three forces. I'm going to make my vector arrows represent the length of these forces. So we have a 20-pound force pulling in this direction, and I'm going to call to the right. This is going to be my main x-axis. So in a lot of problems that you do in real world, you have to sort of pick your x and y axis and then define everything off of that. So here's my x-axis, and this force of 20 pounds is pulling at an angle of 30 degrees. And then I have a force of 25 pounds, and it's going to be pulling at an angle of 40 degrees in the direction that's sort of below the x-axis there. So that would be a negative 40 degrees if we were talking about standard position. And then we're going to put a third vector on, and we're going to put that one on the negative x-axis. So this is going to be 10 pounds. And so essentially we would say that that's at 180 degrees in standard position. So we have three forces. So like, for example, this could be a person pulling something up that way, a person pulling something down this way, and a person pulling back, so like a tug of war. Or maybe this back one could be the friction. You're trying to move this great big couch, somebody's pulling a rope this way, somebody's pulling a rope this way, and the couch friction is just holding it back. So there's different ways that this could model a real problem. So the first thing that we want to do is we want to make sure that we keep track of our vectors, so you always want to label them. So I'm going to label mine F1, F2, and F3. The question I have here is, what is the sum of all these vectors? What is the resultant force? Now this word resultant means the sum of all of the vectors. Especially in physics, when we talk about a resultant force, the resultant is the sum of all of the forces. So the resultant, which I'll call R, the sum of all of the forces, is going to equal F1 plus F2 plus F3. And the R is also going to be a vector. So we know that I can't just add them up and say, oh, well, it's 20 plus 25 plus 10. That does not work. These are vectors. They have directions. So if we're going to add vectors, the easiest way to add vectors is use component form. So I'm going to want to get my F1 and my F2 and my F3 into component form. So I'm going to look at these and I'm going to do them separate here. So if we look at F1, and I'll just draw it by itself to keep track of it. F1 is 20 pounds, that's the magnitude, at an angle of 30 degrees from standard position. So using my formula, I can say that the component form of F1 is going to be 20 cosine of 30 and 20 sine of 30. And so the component form of F1, if you do that in your calculator, is going to be 17.3, and that's in the y direction, if we call our up the y direction. So, that's in the x direction. That's this one. The 17.3 is the x direction. And the y direction is 10. So it's pulling to the right 17.3 and up that way, up 10 pounds. Okay, now we'll do F2. So F2, if I look at F2 in standard position, it's 25 pounds at an angle. Now in standard position, that's negative 40 degrees. And if I write it in standard position, I can use my formula. So I can say 25 cosine of negative 40 degrees and 25 sine of negative 40 degrees. And when I do that, it takes care of the plus and minus signs on my components. So when I do 25 cosine of 40 degrees, of negative 40 degrees, I get 19.9, no, 19.2 rather, 19.2. And when I do 25 times the sine of negative 40, I get negative 16.1. So that negative, I don't have to think about it because I put in the correct angle in standard form. So look, this makes sense. This would be positive 19.2 is my x component, and negative 16.1 is my y component. Okay, now we're going to do F3. Well, F3, you could do sine and cosine, but let's just draw F3 and realize we don't have to do that. So F3 is this way, 10, and so we know the component form is negative 10 comma 0, right? You could do 10 times the cosine of 180, because our standard angle is 180 degrees, and 10 times the sine of 180, right? But we know that the cosine of 180 is negative 1, so this would be 10 times negative 1, and the sine of 180 is 0, so that component would be 0. Now, when I want to find the resultant, well, the resultant is the sum, right? So the resultant, the sum of the three vectors, is F1 plus F2 plus F3. And if I have them in component form, look how easy it is. You just stack those up and add them. And so if I add those up, 17.3 plus 19.2 minus 10 gives me 26.5 for the x's when I add them up. And 10 minus 16.1 gives me minus 6.1 for the y's when I add them up. So that's the answer. That's the resultant. But we were given the problem, we were given all of our forces in magnitude and direction. So let's go back and figure out what our answer is in magnitude and direction, right? So if I sketch my resultant vector, it's 26.5 in the x direction, and it's negative 6.1 in the y direction. And I'll put a negative to mean going down. And so our resultant vector is this. The three of those vectors all combined gives me that one vector. Instead of the three forces acting on the object, this one purple vector would have done the exact same thing. And that one purple vector is 26.5, negative 6.1. So the magnitude of the resultant vector is going to be the square root of 26.5 squared plus negative 6.1 squared. Now just a hint here, a tip. When you're doing the Pythagorean theorem and you're squaring, you don't need to put the negative sign in, because if you put that negative sign in and you don't use parentheses, you're going to get the wrong answer. So I dropped that negative when I put it into my calculator. And when we do that, let's see what we get here. We get the square root, I will do this under here, of 26.5 squared plus 6.1 squared, and see I don't put the negative in, and we get the magnitude of the vector is 27.2 pounds. Now what is the angle of the vector? Well, I'm going to find this angle, right? So the tangent of that angle is equal to negative 6.1 over 26.5. And so if I do tan inverse, second tan, so tan inverse of negative 6.1 divided by 26.5, I get negative 13 degrees, negative 12.96. And so at negative 13 degrees. So that is the resultant vector of those three vectors. Now let's just go back and look at the picture. Does this make sense? So negative 13 degrees would be something like down here. And 26.5 would be something like maybe this. Something like that. So this one resultant vector that's drawn in green, one person pulling that green vector would be the same as somebody pulling 20 pounds this way, somebody pulling 25 pounds this way, and somebody pulling back at 10 pounds. The combination of these three forces adds up and could be replaced by this one resultant vector that we said is 27.2 pounds at negative 13 degrees, which is also the same as 26.5 pounds in the x direction and negative 6.1 pounds in the y direction. And that's how you combine forces when you have multiple forces acting on an object. Resolve them into their components, add their components, and then put it back into magnitude and direction if required.